Hello students, welcome. Today we are going to do a very important topic related to a board's point of view. Very important topic. You will see a derivation or numerical problem from this concept. That is called refraction through spherical surfaces. You see, there are many type of optical devices like lens, convex lens, concave lens, and we can use simple formula to calculate the image distance. For example, if I give you a convex lens, so if I give you the radius or curvature of both the convex lenses, or if I give you the focal length, then you can simply say that if focal length is given to me, object distance is given to me, you can easily calculate the image distance using the lens formula 1 by f equal to 1 by v minus 1 by u. But this formula is not applied everywhere. For example, if you have a paperweight or any kind of, let's say, spherical ball. Now if suppose spherical ball is placed and if light is hitting on the spherical ball from an object, if I ask you to find out the image of that object after passing through spherical ball, then you cannot apply f1 by f equal to 1 by v minus 1 by u in this situation, because it is not a lens, but it will also refract light. So for such type of figure, if you see here, this can be broken into two different parts. So for this we have a topic called refraction through spherical surfaces. So we are going to do this topic today. We will see how an image distance, refractive index, radius of curvature of this surface depends. So this is one of the case. I have drawn one spherical surface, one side of it, it's just like this. Suppose if you have a glass surface like this, something like this, and if light is hitting on the glass surface, something like this, maybe parallelly, maybe make some angle, so it will undergo refraction. So what I am doing is, I have cut one part of that surface and I just kept it like this. So it is the same figure like that. So we will see that the image of this will form, and I assume that this entire medium is a denser medium. So I will see that the image of this object will form somewhere within this region. So I am interested to know where is the image distance and how that image distance depend on refractive index of the medium where object is placed, refractive index of medium where image is formed, and the radius of curvature of the glass surface or any spherical surface. So let us do this. Object is placed at point O, which is on the principal axis. Very standard formula, I am just recapitulating it. You may know how to derive this formula, but this is very important. Then we will do one numerical problem based on this concept. So we must not forget to draw the ray diagram, because arrows are very important. This is the image which is forming here. So object, this is not R, R will be only this much, and let us say this is V. We have to assume, we have to take two assumptions, at least some assumptions here, mainly two assumptions here. The first, and this is very important, it comes in board exam also. What are the assumptions we take while deriving these kind of formulae? So the first assumption we take is that the radius of curvature of spherical surface should be very large. Why? Because we calculate distance from this point, and if radius of curvature is very small, then these 2 points cannot be taken as a single point. We will assume that this point B and this point, let me call this point P, is coinciding, and that coincides when the radius of curvature of spherical surface is very large. When if it is not large, if you see here, if I make this as a glass surface and this is point P here, or this is, let us say, point B here, so now you can assume that this point P and B are coinciding. But if the same glass sphere is of smaller radius, something like this, and if you cut it into two halves, and now you draw a principal axis line, and now if you see here, if you draw a line AB, now you will see that B and P cannot be coincide with respect to this one. So we have to take the glass surface of larger radius, so that we assume that B and P both points coincide, approximation. Second, we assume that all the angles we are taking here are very small, as if light is coming from very far off place, you can also treat like this. So all the angles are taken as very small, then only we will derive an approximate formula to find out the formula, but then at the end it comes out to be nearly equal. So let us see how to calculate this. First of all, since refraction is taking place at point A, So I can use Snell's law at point A. So applying Snell's law at the boundary at point A, in my diagram, or you can also write at the boundary, not a problem, but at point A you can also write boundary. Both are same thing. You can call it boundary, you can call it point A. So if you write it here, then you will write it is sin I by sin R is equal to, since light is going from rare to denser medium, so it will be Nd by Nr, because light is going from rarer to denser medium. And as I told you, all the angles are very small. When all the angles are very small, then you can treat sin I, or you can treat sin theta is equal to approximately tan theta is equal to theta. You can't take it cos theta, because for small value cos will rise, cos will have a larger value for small value of angle. So sin 0 degree will be 0, tan 0 will be 0. So there is no big significant difference between sin 10 degree and tan 10 degree, but on the other hand there is a big difference between cos 10 degree and sin 10 degree. So we take sin theta equal to tan theta equal to theta for a very small value. So therefore this equation can be written as I by R is equal to Nd by Nr, and if I cross multiply this, so I will write I into Nr is equal to R into Nd, and I will make this equation number 1, which will be used after some time. So studio, can you just put it down please, little bit, studio. Now you can take triangles, take triangle ABO. So in triangle ABO we assume that P and B are coinciding, because later on we will find out the relation between UV. So this distance is U. So from this equation we will write tan alpha is equal to AB by BO, and this can be written as AB by PO, assuming that B and P are coinciding. So this will be, and this is, let's say, alpha, because all the angles are very small. Similarly, if you write beta, so beta can be written as, this beta can be written as AB by BC, which can be also written as AP by PC. So I am writing it here AB by PC. You can write AB by BC, but what I am saying is that the B and P are coinciding to each other. You can write AP also here. So if you wish to write the proper form, you can write AP by PO, AB by PC. That's not the problem. Similarly, you can write gamma. So gamma can be written as AB by BI or PI. Now, interesting fact here, if you see, this angle I is an exterior angle of triangle AOC. So angle I is written as alpha plus beta. So angle I is an exterior angle of triangle AOC. So in this situation we can simply write angle I is equal to angle alpha plus angle beta. Now this is my equation number 2. Similarly, if you see in triangle ACI, if you see in triangle ACI, this angle beta is an exterior angle of triangle ACI, which is sum of R plus gamma. So this beta can be written as angle beta is similarly this beta can be written as angle R plus angle gamma. What I need is angle R. So angle R can be written as angle beta minus angle gamma. So this is my equation number 3. Now I will substitute the value of angle I, angle R in equation number 1, which I derived here in this part. So from equation 1, 2 and equation 3, angle I is angle alpha. So I'll just take alpha out. So alpha plus beta into NR is equal to beta minus gamma into ND. Now you can substitute the value of alpha, beta, gamma from these equations. So what do you get? Alpha, which is AB by PO, beta, which is AB by PC. So you can take AB common, and in bracket you have 1 by PO plus 1 by PC, beta 1 by PC into NR. This is equal to beta minus gamma. Beta is AB by PC, so you can take AB out, in bracket 1 by PC minus gamma is AB by PI, so 1 by PI, and again this is ND. So you can cancel AB to AB. Now this is very important equation. You have NR here and you have 1 by PO plus 1 by PC is equal to, you have ND here, in bracket it is 1 by PC minus 1 by PI. Now you see here we have to follow the sign convention very properly. All the distances measured from point P, from this point. Direction measured in the direction opposite to incident light are taken as negative. So light is going from left to right and you are going from right to left. So this distance will be minus u. So this will be negative. This will be positive because you are measuring the direction in the direction of light. So u is negative, r is positive, v is positive. So if I substitute the value here, what will I know? So NR, I'll put NR as it is. 1 by PO will be minus 1 by U. This is 1 by R is equal to ND. This is 1 by R and this is minus 1 by V. So if I just rearrange the terms, so I will get minus NR by U plus this is ND by V is equal to ND minus NR divided by R. Now this is a very important equation. In our equation I have taken ND as a denser medium where image was forming, and R is the incident medium, rarer medium where object was placed. In general you can write it minus N1 by U plus N2 by V is equal to N2 minus N1 by R. Now please understand, it is a very important concept here. What is very important concept is that N1 is the medium where object is placed, N2 is the medium where image is formed, V is the image distance from the point P, U is the object distance from point P, and R is the radius of curvature of that spherical surface, and N2 is again the same thing as I discussed. So this is how you calculate the image distance using given parameters. Let's touch upon one question here, a very important question before I move forward. So let's solve one example, very good example, and this will really brush up your concept in a very effective way. Suppose you have a glass sphere. You have a glass sphere like this. Let's say this glass sphere has a radius, say 10 centimeters. Let's say the refractive index of this glass is 3 by 2 and light ray is hitting the glass slab parallelly, something like this, something like this. So we want to know where is the final image. Find the position of final image. Now final image from where? It is again a point of concern. So let us assume that final image from this point. You can also calculate final image from this point, that's the another issue. So let's first try to understand this qualitatively, what would be happening here. So this is center. If I draw normal, so light would go from, light going from rarer medium to denser medium will bend towards a normal. it will bend towards a normal. So it bends towards a normal, it goes something like this. इसके आगे नहीं ड्रॉ कर रहा, आई एम नॉट ड्रॉइंग नाउ, मैं आगे ड्रॉ नहीं कर रहा, जस्ट इग्नोर माई geometrical error here. What I am doing is, अब if there were no second surface, अगर ये surface नहीं होता, then light would have simply gone straight. This would be I dash. So this I dash is the image formed by first refraction from here. And remember, this I dash is a image formed by first refraction, which I am coming to now. But what is actually happening is that light is also undergoing refraction through second surface, due to which it is again bending. So since it is bending, so it will bend and it will form image somewhere here, because again if you see, this is the normal, so it will bend and it will form here, and this is the image I. Now this is very interesting fact. What is interesting here is that this I dash is the image formed due to first refracting surface. This I is the image formed by second refracting surface. For first refracting surface, object was at infinity. Image is here. Where is object for second refracting surface? So object for second refracting surface is this, which is a virtual object, which we cannot see, right? And this object is in a denser medium itself. It is not outside. That's why I have made it a dotted form. It is inside the denser medium. It is not in the rarer medium. So now you can see qualitatively that this image is forming here at point I, and light is suffering two refractions, one from this, one from this. This is the one form. So by qualitatively, I just draw the diagram and show you that forms here. Let's do it mathematically, whether this approximation or assumption or thought is correct or not. So I will take this as the first refracting surface and this as the second refracting surface. Let's try to understand this for the first refracting surface. So for first refracting surface, you have, so applying the same formula in the first refracting surface, we will use the formula minus n1 by u plus n2 by v is equal to n2 minus n1 by r. In this situation, the distance will be measured from this point P, जहाँ पर light सबसे पहले पड़ती है, from this point P. If you measure the distance from this point P, so n1 is 1 here because it is let's say rarer medium. nr को मैं n1 को I give you 1, assume this as a rarer medium, because right now the value of n doesn't matter. What important point is how we approach to the question. So this u is minus infinity plus n2 is given to me, which is 3 by 2, 1.5. So this is 3 by 2 into v is equal to n2, where the image is formed. Again it is 3 by 2. So 1.5 minus 1, so this is 0.5. So it will be 1 by 2r. And this r will be plus 10. I just skipped one mathematic step here. N2 is 3 by 2, which is 1.5, minus 1.5, 0.5 is half. And r is positive because you are measuring distance from point r. Now if you see this, so you will find that 3 by 2v is equal to 1 by 20, which means v comes out to be 30 centimeter, and this seems to be agreeing with my approximation, because v is 30 centimeter from point P, which is here. Had this image been forming somewhere here, my approximation would have been wrong, because this is 10, this is 10, this is 10, so it is forming on the other side. So v is equal to plus 30 centimeter. Okay, relaxed, I am happy till now. Let's see what happens on the second surface. In the second surface, my point is, let's say, P dash. Now understand here, as I told you, this is difficult to convince, but I told you that this I dash is basically object for second surface, and this is a virtual object. Virtual object you can't see, you will only see the image. You see the real objects and real image. So this is the virtual object, this is the real image. Now virtual object is placed for second surface. For second surface. For second surface, object is placed here. This is u. This is u for second surface. Now, this u is positive because it is in the direction of light. This is 10, this is 10, this is also 10 because total is 30. So, this u is plus 30. Here, object is placed in the denser medium. So, in my case, in this situation, my n1 now is 3 by 2. Because this n, please understand, this n is a refractive index of medium where object is placed. This n2 is a refractive index of medium where image is formed. So, object is placing in a denser medium which we cannot see, it is a virtual object. So, n1 is 3 by 2. n2 where image is forming, which is 1 here, and r is negative because now you are going against the direction of light. You are not in this side but this side. So, r is equal to minus 10 centimeters. Now, let us apply the formula and see whether my approximation goes right or wrong. So, minus n1 by u plus n2 by v is equal to n2 minus n1 by r. And if I use this formula and try to solve it, so n1 is minus 3 by 2 into 30, so which is equal to 60. n1, n2 is 1, v I have no idea what is it. n2 is 1 minus 1.5, so this is minus 0.5 divided by minus 10. Let me check it again. n1 is 3 by 2 here, n1 is a medium where object is placed, here object is placing in a denser medium. So, this is 3 by 2 and u is 30, so this is 60 plus 1 by v is equal to 1 minus 1.5 is this. So, from this what implies? From this you have minus 1 by 20 plus 1 by v is equal to 1 by 20. If you see on this side, so this is 1 by 20. If this is 1 by 20, 3 by 20 minus 100, so this is 1 by 20. So, this comes out to be, I am coming to the next point here. So, 1 by v is equal to 2 by 20. So, v is equal to, oh, I did a little bit mistake here. I just want to correct it. This will be plus 10. So, if this is plus 10, because u is plus 10 here, I did a mistake, just correct it. So, this will be 20. So, if it is 20, so now my equation will be 1 by v is equal to 1 by 20 plus 3 by 20, and this implies 4 by 20, which means v comes out to be 20 by 4, which is plus 5 centimeter. So, I am erasing it. Correct it, u is plus 10, this is plus 10, n1 is 3 by 2, excuse me for this. So, minus n by u plus n2 by v, so this is minus 3 by 20 plus 1 by v is this, so v equal to plus 5 centimeters, and this is plus 5 centimeters from point P dash. So, now you can write in this way that the final image will form 5 centimeters from second refracting surface or 25 centimeters from the first refracting surface, depending on what is given in the question. So, I hope you understood how these equations can be easily applied on glass surfaces. The similar question you can put, if you put objects say at 60 centimeters, you can find the position of image using the same type of formula. Very important numerical for your exam point of view and very important derivation for your exam point of view. Thank you very much for watching. Goodbye.